Math induction is a proof method, and they bring up this well-ordered principle, WOP, for positive. Whenever you see z plus, what's the first value we're talking about? 1. So this is like x is an element of 1, 2, 3, and so on. This well-ordered principle takes a look at all of these whole numbers, and then it starts with the least and goes to the greatest. And so the order is that we do have an order to these, and that helps us with the math induction proof. What the math induction proof is doing is it's giving us some statement, and we're saying it's true for k, or n in this case, greater than or equal to some value z plus. Let's say it's 1, or let's say it's 0. We would never say negative 1, because we're looking at the positive ones. But be careful on that, because it's not always 1. We start with 1 a lot, but not always 1. So P1 is like P of the first value of that has to be true, and then we're showing that if it's true for every step from pk to pk plus 1, then it's true for all n as an element of those positive integers. So I like to describe it like a ladder. Okay, you got to be able to take that first step, P1. If you can't take the first step, you don't have to worry about it. It's done. But if you can take the first step, then the next thing we're looking at are pk to pk plus 1. Okay? Any consecutive step. Now, if this can be determined as doable, that means all of these next steps are doable. That means you can take this step and any other additional step. It's a logical proof, similar to when we did the formal definition of limit. We said there's a relationship between x and epsilon, and then as x got bigger, what did epsilon get? Smaller. Then you had to eventually get an infinite limit. And so similar here. We got to find a first value. If we find the relationship, and then that relationship of next step, if that exists and the first step exists, we can say it's true for every step on the ladder of z plus. So let's just do a couple. I think the examples are good, and you should really take a look at them. But I think it's more valuable just to do problems together. So would you take out your iPads? Okay. So we're going to use math induction to prove that 3 to the n is greater than 7n for n greater than or equal to 3. So for my n, my starting, I like to call it step 1. N equal to starting value. What's my first step? N equal to what? Careful. It's not 1, it's 3 this time. So with n greater than or equal to 3, the first step happens at 3. So 3 to the third, is that greater than 7 times 3? 27 is greater than 21. Therefore, true for P1, or the first value on the ladder. For step 2, I like to write my establishing statement, n equal k. It looks like a waste of time. And, you know, why would you just write this again with, instead of n, you put k in? Okay. But this is going to be helpful as a substitution later. That's why we have it. And most of the time, we're going to use it as a substitution. Pretty much all the time. So then we get to step 3, and this is n equal to k plus 1. So we do 3 to the k plus 1 is greater than 7 times k plus 1. That would be my additional step. Now we need to know a little bit of algebra. What's 3 to the k plus 1? How many 3 to the k's is that? Thank you. I don't know how many times in HL2 I have to go over this, is the 3k times 3. It's 3 to the k times 3 to the 1. So a way to think of it is there's 3 to the k's. What if it were k plus 2? Then it'd be how many 3 to the k's? 9. If it were k minus 1, how many 3 to the k's? 1/3. So that's just a quick way to visualize it. Shortcuts are sometimes helpful. 7k plus 7. Now is where you kind of get stuck. Now what do I do? Well, what we're going to do is we're going to go back to my substitution step and say that 3 to the k is greater than 7k. Now, we're trying to show that this is greater than this. So what essentially can I replace 3 to the k with? Yeah, so we can replace 7k, 3 to the k with 7k. And this is from my step 2. Okay, so now we can go 3 times 7k is going to be greater than 7k plus 7. And if I subtract 7k, I have 3 7k's minus 1 7k. How many 7k's do we have? 2. 2 7k's is greater than 7, right? Okay. And if you want to, I'd solve for k. K is going to be greater than 7 over 14, which is what? 1/2. If k is 3, then 4, then 5, is this always true? Yes. Therefore, true for n equal to k plus 1. Because k is 3 and 3 is greater than 1/2. So then you do your final therefore statement. Since true for n equal to 1 and n equal to k plus 1, statement, actually n equal to 3, statement is true for all n greater than or equal to 3 by math induction. Hooray. I'll continue this until the tricky step. So step 1, you go with, if n is an element of z plus, what's the first value we should try? 1, yep. So it's 5 to the 1 plus 1 plus 2, 3 to the 1 plus 1 is equal to 5 squared is 25 plus 6 plus 1 is 32. Is that a multiple of 8? Yes. So therefore true for m or n equal to 1. And speaking of that m thing, step 2, n is equal to k. You would say 5 to the k plus 1 plus 2 times 3 to the k plus 1 is a multiple. Let's go with a multiple of 8. And you have step 3. So 5 to the k plus 1 plus 1, 2 times 3 to the k plus 1 plus 1 is going to be a new multiple. Oh, let's call it p times 8. most of the time, once the step 1, 2, 3 is laid out, this is where people get stuck, is where do you go from here? You're trying to show that this is going to be true as a multiple of 8. But how do you even get going? Well, what I would do is I would look back at step 2 and realize that we can, that wasn't very nice, we can make a substitution that's going to help us. What do you think up here, what do you think you're going to want to substitute? What's going to make probably the most sense? What are you going to want to eliminate in here? What do you want to eliminate? What don't you like? 5 to the k. So here's what I'm going to do. I'm going to rewrite this first, and then we'll deal with the substitution later. Is rewrite this as how many 5 to the k plus 1s do we have here? Thank you. 5. Good. And how many 3 to the k's do we have here? Yeah, it's 3 to the first times 2 is 6. 3 to the k's. Are you okay with that? Okay with that? P times 8. All right. Now, this thing makes sense to substitute. Okay. So off to the side here, substitute. You're going to say 5 to the k plus 1 is going to be equal to m times 8 minus 2 times 3 to the k minus 1. All right, so 5 times, we're replacing this 5 to the k plus 1 with m8 minus, what is that, 2 times 3 to the k minus 1 plus 6 times 3 to the k plus 1 equals multiple of 8. Like this. So it's 40 times m minus 10, 3 to the k's, minus 5 plus 6 times 3 to the k plus 1 equals p times 8. And 40 times m, what is that? Negative 4, 3 to the k's, minus 4 equals p times 8. Uh-oh. Divide by 8. And so p is going to be 5 minus, what is that? 3 to the k plus 2 over, or plus 1 over 2. And I'm going to do an extra step. Forget I did that. This is going to be 40m over 8 minus 4 times 3 to the k plus 4 over 8. So I'm going to get 5m minus the quantity 3 to the k plus 1 over 2. You're not going to like this. So this is a whole number. This needs to be a whole number. But what's the problem with this? It's not always a whole number. Or is it? Tell me about 3 to the k. Remember, 3 to the k is always odd. 3, 9, 27, 81. Always going to be odd. Therefore, 3 to the k plus 1 over 2 is always what? Always even. Right? Because of an an even number over 2 will be a, I shouldn't say even, is always an integer, because this is going to be an even over 2. So it'll be an, so then you would say, therefore true for n equal to k plus 1. Therefore, since true for n equal to 1 and n equal to k plus 1, the statement is true for all n greater than or equal to 1 by math induction. By the way, how many of you are having trouble with this last part? Is that a little scary? All you do is your first part, n equal 1, second part, n equal k, and what are you trying to do? My statement's true for all n. So there's no magic to that. That is example 2.